Alright, here's the 1.5 video for calculus. And if this is more the pre-calculus review dealing with functions and logarithms. Some of this material we sort of previewed in our exponential function lesson. So we're talking about one-to-one functions. We're talking about inverse functions, how to find those. And we're talking about logs. Logarithmic functions, which are basically those are the inverse functions of the exponential functions that we covered in 1.3. We'll also talk about why we use those and why we use logarithmic problems, like what we can use for applications for those. All right, so a function, again, it's just you give it an input, it gives you an output. So a one-to-one function, though, it can only, even though like a function can usually just have, if you give it any one input, it can only have one output. If it gives you two outputs, for instance, if we kind of sketched a picture of something that's not a function, for instance, if I had a function that looked like that, right, that would fail the vertical line test, so that would fail to be one-to-one. All right, a one-to-one function is it can only have one input and one like it can't repeat either the x's or the y values. So something that's not one-to-one function would be our old friend if you had the graph of x squared. This thing would not be one-to-one because even though it passes the vertical line test, it repeats y values at some point. So if you look at the point 2 comma 4 and negative 2 comma 4, both these x values map to the same y value. So you can say the y's cheat on the x. You can't have that in a one-to-one function. So we don't want to ever have an output value more than once occurring there. So each input is associated with, or each output is associated with only one input. You can't have duplicates. This is the math people definition. You know, if f of a is not equal to f of b, then a is not equal to p. What that basically means is this: the only time that you're ever going to have f of a is equal to f of b, the only time you can have that is if a and b are the same number. So it's kind of a trivial case. So the only time that you can have your y values be the same thing is if it's actually the same x value in here. So it's a really weird definition. It's a lot easier to picture this graphically. You notice how this only has, you only hit -1 once, you only hit 0 once, you only hit +1 once. So this is a one-to-one function. This is not a one-to-one function right here. It's not one-to-one. Graphically, you can see the horizontal line test. It hits, y values. It fails that rule in a lot of places. It only has to fail it in one place. But this thing is not going to be one-to-one. All right? When we're talking about inverses, the reason why one-to-one functions are important when we're talking about inverses is if you took the inverse function of something that's not a one-to-one function, that inverse function wouldn't be a function because if the regular function fails the horizontal line test, well, inverses are basically, you can see it as you're swapping the domain and range. The inverse of this function right here, if I drew this parabola, would actually look like this. So this function's inverse, let's call this f of x. Let's call this f inverse of x. Its inverse function would not be a function because it would fail the vertical line test, which is why we want to make sure that before we take an inverse that we're dealing with a function for starters. So we always want that to be reversed. We want to take an inverse of a function and you still get another function. So you want to go one-to-one function to another one-to-one function there. A little trivial thing is if you compose a one-to-one function with its inverse, it'll send each output back to the input it came from. So it'll kind of give you the identity function is the idea. So here we want to see if this thing has an inverse function. If you want, you can actually graph this in your calculator. So I'm going to do that first, just so we can get kind of a picture of it. We're going to put this function y equals -3 over x plus 7. We're going to put that in our calculators. Okay, so I'm graphing this function right here. All right, putting that in my calculator, and then make sure to put parentheses around your denominator. That's going to be important here. So once I put parentheses around those, I'm going to graph here. You can see you have a little vertical asymptote, which is not surprising because -7 is not in our domain. That vertical asymptote is at -7. My calculator actually graphs the asymptote as a solid line, but that solid line isn't actually there. So mine just shows that your calculators probably won't show this solid line most of the time, and sometimes if you zoom out, it'll fix it. But we want to see if, if we want to see if this thing has an inverse function, it has to be 1-to-1 if its inverse is a function. And this one's going to work out because at no point do the y values repeat. As you're going to the right of -7, your y values are going to just keep going up and approaching 0. They'll never get to 0. You might think like, oh, wait, but isn't this a horizontal line right here? It's not a horizontal line. These values, every time you change x, you're going to change those values slightly. If I go to my table, notice that, by the way, at -7 we have an error. So all my table values, they are going to change constantly, and there's not going to be any repeat values, repeat y values. They're going to change over time. But just looking at the graph, that indicates that this thing is a 1-to-1 function. Therefore, it has to have an inverse. So this is what the graph of our function is going to look like once we graph that. Again, doesn't fail the horizontal line test. You don't have any repeat y values. So this thing, yes, this is going to have an inverse function. A little inside knowledge. You can picture an inverse function graphically a different way. Remember I told you guys about when we talked about odd functions and even functions, how they have this diagonal symmetry. You can sort of see the same thing with with inverse functions. You're actually taking these functions and you're going to you can kind of see it sometimes as like you're flipping it, like you're swapping the domains in the range. So instead of having the point right here, like this point would be, let's go with an easier point to find. So see, this window says -6 in here, so it's 2, 4, 6. So these are 2 right here. There's -7 right here. All right, let's look at this point right here. There's 8, 10. This point is -10, comma. That looks to be about 1.5 or something. I could find out exactly what that value is. The inverse function will be at the exact opposite points. You'd have 1.5 mapped to -10 instead. So you'd swap your domain and range to get your inverse function, and that's why you have to have this to be 1-to-1, because if you fail the horizontal line test in a function, you're gonna fail the vertical line test for its inverse. When we're talking about inverses, again, you'll see this f of -1 symbol. That's how we read f of inverse. It's not a -1 exponent like we usually mean. So f to the -1, if you try to read it as f to the -1, you would think, oh well, x to the -1 is 1 over x. So f to the -1 is like 1 over f, and that's not true. It's coincidental, or it's unfortunate that we use the same notation for that, but it doesn't mean the same thing as negative exponents. Here, negative exponents, when it's like attached to a variable, it does mean reciprocal. Or if it's attached to a number, 2 to the -1, yeah, that is 1/2, but it doesn't read the same way when you're talking about function notation. Composition functions, these, if you take f of g of x, that's going to be the same thing as g of f of x if f and g are inverses of each other. So if you want to see it another way, instead of writing f of g, I'm going to write f of f inverse. Okay? So f of f inverse of x is the same thing as f inverse composed with f of x. Or if you like my notation, f of, I like to do the parentheses in here notation. That's going to be the same thing as if you do f inverse of f of x, like so. So as long as those things are inverses of each other, these are going to actually be the same function there. Well, if you compose something with itself, it gives you the identity function. Now let me give you a very easy example of that. So let's say we have f of x is equal to, let's do x cubed, okay? So, and just to prove it with table values, let's do some easy values. Let's do some x values here. Some, call them the y values, which are the y values, or you can instead put f of x right here, which instead of putting, that's going to be my y value column, right? So if you do -2, for instance, that's going to map to -8 if it's the x cubed function. If you do -1, that's going to map to -1, because if you cube -1, you get that, 0. 1 will map to 1, 2 will map to 8, 3 will map to 27. Okay? The inverse of this function, and here's how we can find that. what you do is you can, I'm going to just for now call this y. All right, so y equals x cubed. What you can do is you can swap your y and your x. So I'm going to put x instead of y here, y cubed here. Now you solve for y. So I'm going to get rid of the y cubed, I'm going to cube root it. You could raise it to the 1/3 power. Usually that's what I decide to do, but I'm not going to do it here just because I'm used to the notation. I want to read that as cube root of x. So the inverse function is the cube root of x. I'm sorry, that 3 should be, here we go. So this is what the cube root of x. This is f inverse of x. So the original function is f of x is x cubed, so your inverse function is the cube root. So whatever this does, your inverse function is going to kind of undo it. So it should make sense that if you compose these two, if you take the number 2 and then you cube it, and then you get 8, right? But then you take that number 8 and you cube root it, well, it's going to spit back out to 2, so it's going to map if you compose f with f inverse, it's going to take what you originally put in, the function, and it's going to spit it back out, so 2 will map to 2 eventually. Now, if we look at, if we want to test if two things are inverses of one another, we can compose them and see if it spits back out the identity function. So you think if you compose, all right, I'm going to do the f of g of x here, so that's going to be square root of, and in place of here, I'm going to put x squared. All right, and that's going to actually spit out just the square root of x squared. Yeah, that's just going to be x. So you would think, oh, well, if I put the whatever x value I put in here, you'll get that back out. But let me show you a little counterexample. Keep this in mind. Think of x squared, all right, the function x squared. That is not a one-to-one function, is it? See, it fails the horizontal line test. Now watch this. What if, for instance, let's do a specific case instead of just a general one. What if you put if you did f of g of, let's do -2. Well, if these are inverses of each other, it should spit back out the value. It should spit back out the value -2. But when you put that into this composition here, I'm doing square root of -2 squared. So this is actually square root of +4, which is going to spit back out 2. So -2 maps to 2, so it fails that whole thing where they should result in the identity function. Whatever you put in, you get out, but it's not going to work out here. And again, that's going to happen because the x squared function is not one-to-one. So finding its inverse is going to be technically a little different. Technically, the inverse, if you think of it, would be sort of, like maybe plus or minus square root of x, which again, then this isn't a one-to-one function, and this one isn't actually a function. Plus or minus square root of x would actually look like that. There's your x-axis, there's your y-axis, if you want to get a visual of that. But when we're writing the inverse of a function, remember, this is the strategy, what we did earlier. We want to swap the x and the y, and then you solve for, after you swap them, you solve for the new y in terms of the new x. And it actually doesn't matter what order you do it in. I could show you it in two different orders, but essentially you're swapping your domain and range, but you always want your x to be your domain value, and it's that new x is the domain of your inverse function, whereas the old x before you swapped was the domain of the regular function. So that's what's going on there. Something else, another way to look at it is, remember I told you that I mentioned that sort of diagonal symmetry? Well, the inverse function it's reflected across the y equal x axis. So you can see your original function is right here. Well, if I just kind of doodle and reflect this across the y equals x axis, by the way, is the line, just a line with a slope of 1 that goes through the 0 of the function. If you kind of just mirror this function, it's actually going to produce your inverse function. But it's actually easier to find it algebraically. So here we have y equals 4x minus 12. And this is, you can write this as y. Now I'm saying that this is our f of x. This thing right here, f of x is equal to 4x minus 12. I want to find f inverse of x. Remember, I don't want to call this f to the -1 power. That's not what it is. It's f inverse of x. And we do that by, I'm going to rewrite this as, I'm going to call this, I'm going to put a little red X here to note that I swapped it, is equal to 4 times Y over here minus 12. And I want to solve for that new red Y. So I'm going to add 12 on both sides. So X plus 12 here equals 4Y, divide by 4 on both sides. So I get my new red Y, the new Y, is equal to X plus 12 over 4. I know if I wanted to, you could even write it another way. You could write Y equals, if you separate them, X over 4 plus 3 if you want to. This looks a little messy too. Well, actually that looks like that's in slope-intercept form, so yeah, I guess that's cool. You could write it as Y equals 1/4 X plus 3. Either of these are okay. I'm going to just go with the slope-intercept. But this is F inverse of X. So F inverse of X is equal to, if you want to write it this way, 1/4 X plus 3. And if you graph these, let's go ahead and actually graph these two so we can have an idea of a visual of what these inverse functions look like. So here I graph those two functions. All right, I'm going to go to my graph, and I can't really distinguish between them right here. So here's what I'm going to do. Let me show you a little trick. All right, you see these little marks on the side here? They all have the same kind of thickness. Now go just to the first one, hover over it, hit enter once. You see how that's thicker right here? Now I'm able to distinguish between, obviously this is my inverse function, and then this is my other one. You could have done it actually before. If you hit the trace button, you can actually tell which is which. You see, right now it tells you you're on the 4x minus 12 one. So if I trace and, walk over this thing, you can see that's the 4x minus 12 one. Then you hit the up arrow, and then it goes to the other one, which, again, I could have actually just looked at my slopes. This one has a slope of 1/4. This one has the steeper slope 4. But I just prefer to get the visual, so sometimes I like to distinguish. There's other little things you can do here besides just a really thick line. You can do shade above. You see how it's shading above there? I see a little live update. You can shade below. This is like the less than equal to equivalent. You can make it do the little ghost thing. Let me show you what that looks like. It actually graphs it slow so you can see it. I find that one kind of cool. And then there's other little things you can do. If you have a TI-84C, you can actually do them in different colors. But so this is you can see if you look here. See how they have that sort of diagonal reflection? If you see that this right here would be the Y equals X axis, which wouldn't it be nice? Let's graph the Y equals X axis by actually graphing the line Y equal X. There it is. You see how this inverse function, it looks a little weird right here. You might think, but it doesn't seem to like it. The window seems a little weird, but remember we talked about our window is wider than it is tall. So I'm gonna zoom. You see this square option? Hit 5, and then that's a little more what you'd expect, isn't it? Doesn't that look kind of perfectly symmetrical about that Y equal X here? So that's the physical change of an inverse to a function. They're reflected across that Y equal X axis.
We'll be right back. We're going to eat some Jello pudding. Da.
The views and opinions expressed in this video are solely those of Mr. Vogel and do not necessarily reflect those of the School of Sacred Heart, Edward Coteau, its board of directors, administration, and network Sacred Heart Schools, or anyone else. Visit our website at shhcoteau.org.